In the coating industry today, the use of through-process temperature monitoring has become very important in maintaining the quality of both powder and painted coatings. Understanding the temperature of your product as it travels through the curing oven is essential to ensure that you get the right thermal conditions to cure that coating properly. When we consider the word cure, we have to consider the fact that we're really talking about a chemical reaction. In most coating systems, we're talking about the polymerization or the cross-linking of the material, which is activated by temperature, and the reaction time is related to the time that the product spends in the oven. As you can see from the following slide, the coating manufacturers will recommend what they call a stoving schedule or a curing schedule to achieve the best quality for the coating. As you'll notice on the datasheet highlighted on the slide, there are a number of different cure schedules that can be used to quantify the success of the curing process. 170, 180 and 200 degrees with different durations. Because it's a chemical reaction, the higher the temperature, the quicker the reaction will occur. The lower the temperature, the lower the chemical reaction will occur. So you can control the curing by controlling the temperature of your oven, but you need to know what your product temperature is to satisfy these conditions. The temperature profile you can see in front of you now is a typical, very basic powder coating profile. You'll notice that we are performing a calculation of time at temperature to determine whether we're achieving the correct cure schedule recommended by the coating supplier. 25 minutes at 170, 12 minutes at 180, or 8 minutes at 200 degrees. On the analysis table, you'll notice that for each of those temperatures, the time the product spent above those respective temperatures are lower than the required cure conditions. Under these circumstances, you would often jump to the conclusion that your coating is undercured. The problem we have to address, though, is that from the whole profile, there is a whole series of different combinations of time and temperature that are going to affect the actual curing of the coating. If you see here above 200, we actually have the product experiencing temperatures very close to nearly 220 degrees, where the chemical reaction would be very fast. And this information is excluded basically from the calculations at a simple time and temperature level. To reiterate the problem, here we have a schematic of a very simplistic profile. We have two traces, one red and one green. If we want to measure the time and temperature at 180 degrees, you'll notice that both traces, the green and the red trace, both have a time above temperature of 10 minutes. This is less than the 12-minute target that we're trying to achieve. From common sense, though, you can see that the green trace exceeds the upper maximum limit of the red trace significantly. So you would expect the cure of the green trace to be significantly higher than the red trace. But if we quantify purely at 180 degrees, we will get a numerical analysis result that implies that both traces are cured the same. This shows you the weakness of performing just time at temperature calculation in a temperature profile situation. We need to be able to look at all of the data on the profile trace and see what the combination of that data is to the total cure of that coating. This leads us to the use of a calculation from Phoenix temperature measurement that we refer to as the Phoenix factor. And I'll now explain how that works in principle. On the first slide, we saw the datasheet for a coating with 3 specific cure schedules: yellow, green, and blue. If we plot those on a temperature time trace, you can see that we have unique cure conditions at those 3 temperatures. But if we fit an exponential line to that data, we now have the means by which we can interpolate the required time at any curing temperature. As you see on the graph at the moment, if I was to take a value of 201 degrees Celsius, from interpolating that onto the graph, I can then estimate or approximate that the time or the cure time required at 201 minutes is 7.16 minutes. This graph fits in with the cure conditions of the chemical reaction that we're performing when we're curing paint or powder coatings. And it's referred to as the Arrhenius relationship. So for the first time, we can now discover or calculate the required cure conditions at any temperature over the total profile that we're running. This information is critical to us calculating the total combined cure conditions for the powder or the paint that we are processing. From that exponential graph, for instance, we can take, this is our red trace, a single profile shape. In practice, what we're doing with the calculation is we're going to take a little subset of that profile. So this is 5 seconds at 201 degrees Celsius. We know that our midpoint cure schedule is 12 minutes at 180. The question is, can we convert the 5 seconds at 201 degrees Celsius to an equivalent time at 180, which we know is a nominal cure schedule of 12 minutes. From the previous slide where we had the exponential curve, we identified that at 201 degrees, the cure schedule would be 7.16 minutes. So from this simple calculation here, we can work out that 5 seconds at 201 degrees is equivalent to 8.38 seconds at 180. We've just done that for one sample interval measured from the Phoenix data logger from our profile graph. We can then repeat that process for the whole of the profile, converting each and every different 5 seconds at a temperature to an equivalent time at 180. In essence, having done that, we can get the complete summation of contributions from every measurement and calculate the equivalent time at 180 degrees. Remember, our total time at 180 degrees needs to be at least 12 minutes to get the satisfactory cure. If our total summation of the contributing time and temperature components in the profile is exactly 12, that would mean we are matching the cure schedule exactly. That would give us a perfect theoretical cure, which we refer to as a Phoenix factor of 1. Our profile matches exactly the required cure schedule from the coating supplier. If the equivalent time is less than 12 minutes, we would then have a Phoenix factor significantly less than 1, implying undercure. And if the total equivalent time is greater than 12 minutes at 180, we would then have a Phoenix factor of greater than 1. The Phoenix factor is basically the theoretical equivalent time at 180 divided by the target cure time. So this is a simple mathematical manipulation of the profile data to give us a total equivalent time at a nominal temperature, which is generally the midpoint cure schedule. So within the software, the Phoenix thermal view finishing software, we have the feature, as I've mentioned before, referred to as Phoenix factor. On this Phoenix factor table, you can see that we have the 3 cure schedules that we put in as our target cure schedule information. The software will then calculate from the profile the maximum temperature and also the equivalent time at the midpoint cure schedule value. You'll notice here that if we do a simple time at temperature at 180, our target is 12 minutes. We've got 9 minutes 39, 8 minutes 10, 9 minutes 35, and 8 minutes 52. Each one of those is less than the required target cure schedule at a nominal 180 degrees. Taking all of the data from the profile, though, we're calculating that our theoretical equivalent time at 180 is 17 minutes 23, 13 minutes 57, 17 minutes 60, and 15 minutes 60, which is greater than the 12. So you can see here that we're calculating a Phoenix factor which is higher than 1. So we have proven that we have the successful cure conditions, and this is then represented both numerically in the table and also graphically. Our target for our Phoenix factor that we've set up is between 1 and 1.6, so we don't want an undercure in any way whatsoever. There is some overcure protection in the coating system itself, so we believe that we can tolerate up to 1.6, a Phoenix factor of 1.6 or lower. The parameter table where we set up the Phoenix factor is shown here on this slide, but I'm going to go through that in a little bit more detail on the next slide. In the Phoenix thermal view finishing software, we have our coatings library where you can set up for each of your coating the specific parameters for the use of Phoenix factor. As I said before, what you would do is you would set up a library name or a coating name which is unique to the actual coating that you're monitoring. We put in our cure schedules, so 170 at 25, 180 at 12, and 200 for 8 minutes. You can put up to 10 different cure schedules if you wish. The other important information we need to put into the system is the cure activation temperature. This is the temperature at which the cross-linking will commence. The maximum temperature, which is a temperature you don't want to go above, because in some circumstances, an excessively high temperature may cause other problems to the coating, like discoloration of color. It may actually start to damage the surface of the coating, or it may even damage the actual substrate that the coating is applied to. We can set up the range of successful or acceptable Phoenix factor values we're looking for, and you can, as I showed in the previous table, report the calculated equivalent time. The 3 cure schedules that we put into the parameters dialog then creates this graphical view of the exponential line fit that we can put to this data. It is possible, though, to change the line fitting algorithm that you're using. There's multi-exponential, single exponential, and linear. But the numerical data here will show you what is the best fit to the data that you're using for your run. This information is stored in the finishing software package, and you can apply it to the profile run that you have performed. I will show how this works in practice with the software in the later stage of this video. So, in summary, what are the benefits of the Phoenix factor for through process temperature monitoring of your cure process? The benefit is primarily that we are able to, with a single numerical value, identify under cure or overcure problems instantaneously in the software. This gives accurate setup of process settings to achieve quality and efficiency. You can monitor the Phoenix factor over time. So if your process starts to deteriorate, you will see that by a change in that single Phoenix factor value. Setting up different paint lines, you can compare the Phoenix factor from one line to another, irrespective of the shape of the profile. The full numerical analysis that Phoenix factor gives you will allow you to compare one line with another, even from plant to plant if that's important. And it meets all the Qualicoat analysis and reporting requirements you may need. The software has been uniquely developed to give you full flexibility over controlling the Phoenix factor calculation with 3 cure fitting options, a full graphical and numerical display of how the line fits to the data. You can use up to 10 cure schedules if you wish, but in most cases people will use 3. The constant cure curve created will show you the actual regression statistics for the line to see whether it is the best fit to the data that you're using. And the software will not only give you the Phoenix factor, but it will also tell you the equivalent time at the midpoint cure schedule that's being used. So you've got the direct time at temperature information if that is helpful in your optimization strategies. And at the last but not least, the Phoenix factor is easy to interpret using both numerical and the graphical pass-fail indicator tool. So let us now see how the Phoenix thermal view finishing software works with specific focus to the Phoenix factor analysis. I've opened up in the software package a standard powder coating run, and it's very simple. It's only 4 channels. If I click on the probe thermocouple location label, you can see here that we're doing an aluminium gutter, and the thermocouples are positioned. 1 is oven air top, 3 is oven air bottom, 2 is product top, and 4 is product bottom. So very simple in practice. And you can see here from the trace, the red and the blue traces are the 2 air probes with the noise you would associate with the convection within inside the oven. And then the green and the orange traces are the product profiles, top and bottom respectively. Now, as we were talking in the earlier part of the video, we can quite easily look at the raw data, but also probably the most common method of quantifying the profile is using the time at temperature analysis, and you can do that. And I've put in here the 3 cure schedules that were relevant for this particular powder coating that's being profiled. The cure schedule at 180 degrees is 10 minutes, and you can see here that clearly none of the traces actually achieve that cure schedule at all. So you could jump to the conclusion that we're actually undercuring this particular powder coating. And that's where the Phoenix factor comes into its own, because what we're going to do now is take all of the information from the profile and numerically analyze each and every sample interval to give an equivalent time at that nominal cure temperature of 180 degrees Celsius. So if I go to the coatings library, what I've done is I've set up a coating called Awfully Powder Coatings, and in there I have set up our cure schedule information to allow us to use the Phoenix factor. So it's very simple in practice, and all this information will be provided by the coating supplier in their coating datasheet. So you're just transposing the data directly from that datasheet into the software. So for this particular powder coating, we have our 3 cure schedules, 1, 2, and 3, 170 at 25, 180 at 12, and 208 8 minutes. The cure activation temperature, I know for this coating is 160, so I've just put that value in. And I don't want to exceed 220 degrees, because I know above that temperature we could risk potentially damaging the cosmetic appearance of the coating. Classic example would be a red will turn to an orange, or a white will go creamy in color. Or if we were dealing with plastics, obviously you wouldn't want to be running at that sort of temperature because of distortion problems. For this particular run, I've set my target Phoenix factor to be between 1 and 1.6, but if I wanted to, I could change that to 2. And I would like to report the equivalent time at the midpoint, which is 180 degrees in my calculation. So the 3 cure schedule values are then shown on this isocure or constant cure curve. And at the moment, I'm fitting the data using a multi-exponential curve. So there's one exponential fit between 2 data points, and then a separate exponential fit to give my graphical cure line as shown. I could, though, use a single exponential fit, or if necessary, a linear fit. And it's down to you to select which you want to use. But I'm going to use the default, which is multi-exponential fit. And you can see here how well the line fits the data, and the regression statistics for that fit is shown on the screen. So simply, we're going to use this constant cure curve to analyze all of the profile data in our temperature profile run and give us our Phoenix factor result. So if I now go to the Phoenix factor section of the analysis tabs, you'll notice that now for my analysis screen, I have all of the data associated with the Phoenix factor calculation. For each one of the thermocouples, I've got the actual nominal time at temperature calculated for the 3 temperatures. And you'll notice here that, sorry, as before, I was saying that the cure schedule was 10, it's actually 12 minutes. So it's even worse than before. So although at 180 degrees, we're not achieving our unique cure schedule of 12 minutes, 9 or 8 minutes respectively, if we take all of the analysis data using the calculation from the constant cure curve, you can see here for each one of the thermocouples, we've got an equivalent cure time at 180 to be calculated at 17, 13, 17, and nearly 16 minutes respectively. And each one of those is higher than the minimum required 12 minutes. So we are now able to prove that for the whole profile, we have actually achieved our minimum cure conditions, and that generates a Phoenix factor as shown in the table. So in each case, we're exceeding 1, so we've achieved our minimum requirement, but we're not over curing significantly. On the pass-fail traffic light indicator, you can see here that each one of the thermocouples is within our pass-fail conditions of Phoenix factor of 1 to 1.6. So in essence, it's as simple as that. A way by which you can use all of the data from the trace to give you an accurate combined cure condition or analysis result for your profile. So that shows you how easy it is to do the analysis. And if you wish to document this, we would simply go to our print report and we set up all the parameters that we need, all the documentation to explain how the test was performed. And I'm just going to pick a simple one-page analysis report with Phoenix Factor and with the Phoenix Factor chart selected. Click Create Report, and you'll now see that we have our fully traceable profile report showing the graph data, the full analysis for Phoenix Factor, plus the Phoenix Factor traffic light pass-fail indication, and all of the traceable documentation to prove how the test was performed and the conclusions that were taken from it. So I hope that proves useful to you in explaining how the Phoenix Factor can be a very useful tool in making your through process temperature profiling runs easy, efficient, and accurate. And at the end of the day, come to the conclusions that allow you to maximize the efficiency of your paint cure processes.